Now, let's look at the second rocket equation. We want to get the velocity change, how can we get in terms of the relative velocity? Okay. And this one, this one actually is straightforward. So we already have the first rocket equation, ma equals to r relative, v relative. And this is, you can think about, if we know, when we do the Newton's second law, if we know, like say, ma equals to f net, and if we want to find the velocity, we just go write it as m dv over dt equals to f net and integrate it to get the velocity, right? That's the standard procedure. But there, the external control is the force. And here you can see it looks quite similar to that, right? Mass multiplied by acceleration equals to some external control. But in this case, the external control is not this engine force or something like that. It's a relative velocity, right? So you are doing the same thing. And, so let's see, let's write this as capital M dv over dt equals to r relative v. Okay. And if we want to integrate it, we have to write this m. We want to multiply by dt over dt and both sides. Okay. So we get m dv equals to r relative dv multiplied by dt. Okay. And then we have the v equals to r multiplied by v relative divided by capital M multiplied by dt. Okay? And now we have to do some trick here. If we just directly do that, we're going to get this side, we're going to integrate it to get velocity change. This time, it seems that we want to integrate with time dt, but from a practical point of view, this is not very useful for us. We want to integrate it with mass, because usually we directly calculate the mass change. How can we integrate this with mass? You can think about r. The original definition of r is dm over dt, right? And we just argue that it's also negative d capital M over dt, right? Okay? So if we substitute r by negative d capital over dt, you can see what we get. So this side we get negative d capital M dt multiplied by v relative divided by capital M over dt. So this dt cancels this dt, and you have a differential for dm. Okay. This one is very hard to integrate at this point, because unless you know the mass, as you know the functional dependence of the mass on the time t, you cannot evaluate this integral, right? Because the mass is changing, it's a function of time t, but you don't know the dependence right now. So we change it back to the variable mass itself. This integral can be done. Okay. So after this manipulation, we get dv equals to negative v relative dm over m. Okay? And this is some integral we can do. This side, and if you integrate we do definitely integral. So initial velocity to final velocity. This side is definite integral from initial mass of the rocket to the final mass of the rocket. M over M. And we know how to do this kind of integral, right? And this side, what you get? V final subtract V initial, right? And this side, you still know how to do it. It should be yes, okay. The integral of, if you have x, remember what you get for this integral? Natural log, okay. Natural log m, okay, from initial mass to the final mass, okay. And this side is already the left-hand side of the rocket equation. And let's look at left-hand side. Look at what's going on with the right-hand side.
On the side with the velocity, isn't that the integrated v final and v initial?
This is just integral this. If you have like integral 1 dx, what do you get? You get x from initial value to the final value, right? So this is x final minus x initial.
Right.
And so here you get v final minus v initial. See. And this equals to negative v relative. This one is log m final subtract log m initial, right? Okay, substitute the initial value, final value. And remember, what is, okay, rewrite this. If you kill the negative side, it becomes v relative log m initial minus log m final, right? Okay? Now, remember, for the logarithmic function, you have an important identity. Log x minus log y. What's that? It's log x over y. So then we get v final minus v initial equals to v relative log mi over m final. Right? You did correct? Okay, so that's it. So this one involves a lot of different parts we learned before, okay? Because that's a very realistic problem. So you can see stuff from here to there, you need to use a lot of knowledge we learned before. Any question here? And there are the two fundamental equations when you do the calculation for the rocket. When you design the rocket, you definitely need these things. Okay?